In this video, we will talk about what complements, intersections, and unions are. So these are going to be ways for us to construct new sets from a given set. And I want to begin with a definition. So we say that a set U is the universal set if all sets in the problem are subsets of U. So usually in a question, the set U, the universal set, is going to be specified for us. Alrighty. And then if A is a set, then the complement of A is the set of all elements that are in U but not in A. And we're going to denote this with A and put a little apostrophe on it. So one thing I want to mention about the spelling here is notice that complement here is spelled with the letter E. When you spell complement with an I in that spot, that means to praise. To give somebody a compliment, to praise them. But okay, yeah. Okay, so a little bit of a mini English segue there, or digression. So there's a couple of other ways that a complement is often notated. So this is also sometimes written as A with a line over it, a bar over it, or we could write A with a little C where the exponent would be. That also means complement. But I'm primarily going to be using the notation with the apostrophe. So let's do an example. So in this example, we have these three sets. Okay, and U is our universal set. So notice that this is given to us in the problem. And each of these sets contains some US states. And part A asks to find the complement of A. So let's recall that the complement of A with this apostrophe, it's the set that contains all the elements that are in U, the universal set, but not in A. So the complement is a way to describe all the elements that are not in A, but still within our big universal set. Alrighty, so what are all the things that are in the universal set but not in A? Basically, I need to throw out the California, throw out the Hawaii in the universal set. And that'll leave us still with Oregon, Washington, Alaska, and Alabama. Those 4 states. Those are all the things in our universal set that are not in the set A. So that is the complement of A. Okay, let's do another example. Now let's find the complement of U, the complement of the universal set. So doing the same thing, the complement of U is the set that contains all elements that are in U, the universal set, but not in U. And that's a little bit weird. What are all the elements that are in U, but also not in U? Well, there would be no such elements, because something can't be in U, but also not be in U at the same time. That would be a bit bizarre. So no such elements. There's actually an interesting paradox about sets involving elements being in a set, but also not being in it, which we'll talk about later. So for right now, let's just focus on this example. So because there are no such elements here, we say that the complement of U is the empty set. That's what a set is called when it has no elements inside it. And the notation for this is we would write U complement equals, we put this circle and a slash through it. And that's the notation for the empty set. All right, so I want to make a couple of short comments. For any set S, it turns out that the empty set is always a subset of S. And S is a subset of itself. So I'm going to put this in a little bubble here. So it might be weird to see or to think about the fact that the empty set is a subset of S, but I'll try to briefly explain why that is. The only way something like A would not be a subset of B, so when I write something like A is not a subset of B, the only way for that to happen is if there's something in A that's not in B. So this happens if there's an element in A that's not in B. And I'll put that in a little thought bubble. But with the empty set, there's nothing in it. So I can't find an element that's in the empty set that's not in S. So it would be untrue to say that the empty set is not a subset of the set S. And as a result, that means the empty set is a subset of S. Okay. All right, so I want to give another definition for two other set operations. So these are intersection and union. And you may have seen these before in previous math classes. But the intersection of sets A and B is the set that contains all elements that are in both A and B. And this is denoted as A, we put an upside down U, B. I could also describe this with a rule. So I could write A intersection B, that's how I read that. A intersection B is the set of all X such that X is an element of A and X is an element of B. That's how I would write intersection with a rule. So the word intersection refers to the English word and. You got to be in the first set and the second one to be in the intersection. Okay, the union of sets A and B is the set of all elements that are in A or in B or in both. And this is denoted with an A and then a U shape, and then B. If we were to write this with a rule, we'd write A, that U shape, B. So we read that as A union B equals the set of all X such that this time X is in A or X is in B. So I want to give a bit of terminology here. This or that we use to describe the union is what's called an inclusive or. Because in English, in the English language, sometimes when we use the word or and we say like something or something, we mean either the first thing or the second thing, but not both. That's called an exclusive or. You can't be in both. But sometimes in the English language, when you say the word or, you do mean to include the possibility that you could also be in both. That's also okay. So in the case of union, when we say the word or, it's an inclusive or, meaning we're in the union if you're in the first one, or in the second one, or in both. So let's continue our example and find A intersection Z. Okay, so let's recall the definition. So A intersection Z is going to be the set that has the elements that are in A and in Z. They got to be in both of them. So A intersection Z is equal to, let's look back to our example. So A had California and Hawaii, and Z has California, Washington, and Alabama. And the only element that's in both is California. So that's what's in the intersection. So A intersection Z is the set that has the element California in it. That's the only element that's in both A and Z. Next, in part D, let's do the union. So recall that the union, A union Z, would be the set that has the elements that are in A or Z or in both. Okay, so what are the elements that are either in A or in Z or in both of them? So looking back to our example, so A has California and Hawaii. We for sure got to include those. And then in Z, we have California, Washington, and Alabama. So we got to include those. Overall, there's 4 states here that are in at least one of them. California, Hawaii, Washington, and Alabama. California is actually in both of them, and that's fine. That still means you're in the union. So let's list out those 4 states. Okay, so the union. Sorry, just shifting it over here. All right, so the union has California, Washington, Hawaii, and Alabama. Those were the states that were in at least one of those 2 sets. They're either in A or Z or both. Okay, part E asks, well, let E be the set Alaska and Oregon. It has both of those. Find A intersected with E. So let's zoom it out. What was in A? A had California and Hawaii. And E has Alaska and Oregon. So the intersection is the stuff that's in both. A intersection E. But what's in both of them? Well, nothing's in both of them. So their intersection has nothing in it. So we would say it's the empty set. And I want to end this video by stating a definition related to this last part of the example. So the definition says that if A intersected with a set B is the empty set, we have a word that we use to call these sets to describe them. We say that A and B are disjoint. They are disjoint sets. In the next section, when we talk about Venn diagrams, we'll see that disjoint sets are situations where there's no overlap in their 2 circles. But we'll see that in the next section when we talk about Venn diagrams. Okay, so in this example, A and E have no common elements, so they are disjoint. So in the next video, we will talk about another way to form new sets from given sets, and that's what's called a Cartesian product.